Imagine a particle that is, in almost every measurable way, identical to the electron. Same mass, same spin, same magnitude of electric charge. It obeys the same laws of physics. It exists in the same universe, made from the same quantum fields. And yet, the instant it touches an electron, both particles vanish. Not broken apart, not scattered, not chemically transformed. They simply cease to exist as matter, and in their place, a burst of pure energy erupts outward at the speed of light. No ash, no residue, no fragments left behind, just light. This is the positron, and the question that should bother you is not just what it is, but why. Why would two particles that are nearly perfect mirrors of each other be unable to coexist in the same space? The answer reaches into the deepest structure of reality itself. Before we go any further, if you find these deep explorations of physics fascinating, a quick like or subscribe genuinely helps the channel grow. It's a small thing on your end, but it makes a huge difference for me. Now, let's begin. Let us start with something you already know, even if you have never thought about it in these terms. Everything around you, the screen you are watching, the air filling your lungs, the bones holding you upright, all of it is built from matter. And matter, at its most basic level, is built from atoms. Atoms themselves are built from just three types of particles: protons, which carry a positive electric charge, neutrons, which carry no charge at all, and electrons, which carry a negative charge. Protons and neutrons sit together in a dense core called the nucleus at the center of the atom. Electrons exist in a cloud around that nucleus, bound to it by electromagnetic attraction. The positive protons pull the negative electrons inward, holding the atom together. This is the architecture of ordinary matter. It is the foundation of chemistry, biology, and everything you experience in daily life. Now, of those three particles, the electron holds a special place. It was the first subatomic particle ever discovered. In 1897, the physicist J.J. Thomson found that cathode rays, streams of particles produced inside vacuum tubes, were made of tiny negatively charged objects, far lighter than any atom. These objects were electrons. That discovery shattered the idea that atoms were indivisible. They clearly had internal parts. The electron turned out to be extraordinarily light. Its mass is roughly 9.1 times 10 to the negative 31 kilograms. That number is so small, it borders on meaningless in everyday terms. But here is what matters. The electron is about 1,836 times lighter than a proton. It is a tiny thing, carrying a single unit of negative electric charge, orbiting the atomic nucleus at speeds that are a meaningful fraction of the speed of light in heavier atoms. And as far as every experiment we have ever performed can tell, the electron has no internal structure. It is not made of smaller pieces. You cannot crack it open and find components inside. It is, in the language of modern physics, a fundamental particle. It is one of the bedrock building blocks of reality. You might assume that once you understand the electron, you have understood everything there is to know about lightweight charged particles. But nature had a surprise waiting. A surprise that emerged not from an experiment, but from an equation. In the early 1920s, physics was undergoing a revolution. Two extraordinary theories had appeared within the span of a few years. The first was special relativity, published by Albert Einstein in 1905. It showed that space and time are not absolute, that nothing can travel faster than light, and that mass and energy are interchangeable through the famous relationship E equals mc squared. The second revolution was quantum mechanics. Pioneers like Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and Max Born had developed a framework describing how particles behave at atomic and subatomic scales. Quantum mechanics was strange. It said particles do not have definite positions until measured. It said energy comes in discrete lumps called quanta. It described the electron not as a tiny ball orbiting the nucleus like a planet, but as a probability cloud, a smeared-out wave of likelihood. Both theories were confirmed by experiments. Both made predictions that matched observations with astonishing precision. But there was a problem. They did not agree with each other. Quantum mechanics, in its original form, did not account for special relativity. It worked well for electrons moving slowly, but when electrons moved at speeds close to the speed of light, the equations gave wrong answers. The two greatest achievements of early 20th century physics were fundamentally incompatible. Someone needed to combine them. That someone was Paul Dirac. Dirac was a British theoretical physicist, quiet and precise, famous for saying almost nothing in conversation, but writing equations of extraordinary elegance. In 1928, Dirac published a new equation for the electron. His goal was straightforward. He wanted an equation that described the electron's behavior while obeying both quantum mechanics and special relativity simultaneously. He wanted the best of both theories in a single mathematical framework. And he succeeded. The Dirac equation, as it came to be known, was a masterpiece. It described the electron in a way that was fully consistent with special relativity. It automatically predicted the electron's spin, a quantum property that earlier theories had to insert by hand. The electron has a spin of 1/2, meaning it behaves in a particular way under rotations. Previous equations could not explain why. Dirac's equation produced spin 1/2 naturally, as an unavoidable consequence of the mathematics. It also correctly predicted the electron's magnetic properties, the way an electron behaves like a tiny magnet. These were not things Dirac put into the equation. They came out of it on their own, as logical consequences of combining quantum mechanics with relativity. The equation was beautiful, but it had a problem. A very strange, very deep problem. When Dirac solved his equation for the energy of an electron, he got two sets of solutions. One set described electrons with positive energy. These were ordinary electrons, the ones we know, the ones orbiting atoms and flowing through wires. The mathematics described them perfectly. But the second set of solutions described something with negative energy, and that made no physical sense. In everyday life, energy is always positive or zero. A ball sitting on a table has energy. A ball rolling across the floor has more energy. You can take energy away from a system, but you cannot push it below zero into negative territory. Negative energy states should not exist. If they did, an ordinary electron could radiate away energy and fall into a negative energy state, releasing an infinite amount of radiation in the process. Atoms would be unstable, matter would collapse. The universe as we know it could not exist. Most physicists would have looked at these negative energy solutions and dismissed them as mathematical artifacts, quirks of the equation that do not correspond to anything real. But Dirac did not dismiss them. He took the mathematics seriously. He believed the equation was telling him something true about nature, even if he did not yet understand what. And so he proposed something radical. This was not a casual decision. Dirac spent months struggling with the negative energy solutions. The obvious move, the move that most physicists would have made, was to simply ignore them, throw them out, declare them unphysical artifacts of the mathematics, and move on. After all, equations often produce solutions that do not correspond to reality. When you solve a simple equation for the trajectory of a ball thrown into the air, you get two solutions. One describes the ball going up and coming back down. The other describes the ball travelling backward in time, arriving from infinity. You discard that second solution without a second thought. It is mathematically valid, but physically meaningless. Dirac could have done the same thing with his negative energy states. Many of his colleagues urged him to do exactly that. But Dirac was different. He had an almost religious faith in mathematical beauty. He believed that if an equation was elegant enough, if it arose naturally from fundamental principles, then all of its solutions must mean something. Discarding half the solutions would be like tearing pages out of a book because you did not understand them. The equation was too beautiful and too successful in its positive energy predictions for its negative energy predictions to be meaningless noise. Something real had to correspond to those solutions. The question was what? The depth of the problem cannot be overstated. If negative energy states existed and were empty, ordinary electrons would immediately radiate energy and cascade downward into them, releasing infinite amounts of radiation in the process. Every atom in the universe would collapse in an instant. The fact that atoms exist and are stable meant that either the negative energy solutions were wrong, which would undermine the entire equation, or something was preventing electrons from falling into those states. Dirac needed a mechanism to block the collapse. He needed a reason why electrons could not simply tumble into the negative energy abyss, and he found one in a principle that was already well established in quantum mechanics. The Pauli exclusion principle, formulated by Wolfgang Pauli in 1925, states that no two identical fermions can occupy the same quantum state simultaneously. Fermions are particles with half-integer spin, and the electron, with its spin of 1/2, is a fermion. If two electrons cannot share the same state, then a third electron cannot enter a state that is already occupied by two. This is the principle that gives atoms their structure, that determines the arrangement of electrons in shells and orbitals, that ultimately explains the periodic table of elements and all of chemistry. Dirac realized he could use this principle to solve his problem. If every negative energy state was already occupied, already filled with an electron, then the Pauli exclusion principle would prevent any additional electron from falling in. The collapse would be blocked. The universe would be stable. Dirac imagined that the vacuum of space, what we think of as empty nothingness, is actually not empty at all. Instead, he proposed that every negative energy state is already filled with an electron. All of them. An infinite sea of negative energy electrons filling every possible state, completely invisible to us because the sea is uniform and undetectable in its ground state. You cannot see it for the same reason you cannot see the air pressure around you. It is everywhere, constant, and your instruments are calibrated to treat it as the baseline of normal. But here is where the idea becomes extraordinary. If one of those negative energy electrons were somehow knocked out of its state, if enough energy were added to promote it to a positive energy state, it would leave behind an empty spot in the sea, a hole. And Dirac realized that this hole would behave, from every observable perspective, like a particle. A particle with the same mass as the electron, the same spin as the electron, but with opposite electric charge. Where the electron carries negative charge, the hole would appear to carry positive charge. This was an incredible prediction. Dirac's equation was not just describing the electron, it was predicting the existence of an entirely new particle, a mirror image of the electron. Same mass, same spin, opposite charge. A particle that had never been observed. A particle that no one had even imagined before the mathematics demanded it. Now, Dirac initially hesitated about what this particle might be. In 1930, he briefly speculated that the hole might correspond to the proton, the only known positively charged particle at the time. This would have been elegant. It would have meant the universe needed only one fundamental charged particle, the electron, and its absence in the negative energy sea would appear as the proton. But this idea fell apart almost immediately. Robert Oppenheimer demonstrated mathematically that if the hole had a different mass from the electron, if it were as heavy as a proton, then ordinary hydrogen atoms would annihilate themselves almost instantly. The electron orbiting the proton would fall into the hole, both would vanish, and the atom would be gone in a tiny fraction of a second. Since hydrogen atoms obviously exist and are perfectly stable, the hole could not be the proton. The mathematician Hermann Weyl reached the same conclusion independently. The hole had to have exactly the same mass as the electron. It had to be a new particle, an anti-electron, something nature had kept hidden from us, lurking in the mathematics of the most elegant equation ever written for the electron. And then, in 1932, someone found it. Carl Anderson, a young physicist working at Caltech, was studying cosmic rays. Cosmic rays are high-energy particles that slam into Earth's atmosphere from space. They come from violent astrophysical events, exploding stars, active galaxies, and other extreme environments across the cosmos. Anderson was studying cosmic rays for a reason that reveals something important about the state of physics in the early 1930s. If you wanted to observe high-energy particle interactions, you could not simply build a machine to produce them. Particle accelerators existed at the time, but they were primitive devices, cyclotrons and electrostatic generators capable of accelerating particles to energies of a few million electron volts at most. That was enough to probe atomic nuclei, but nowhere near enough to create new particles from energy. To produce an electron-positron pair requires at least 1.022 mega-electron volts concentrated in a single interaction. The early accelerators could barely reach that threshold, and doing so reliably and controllably was beyond their capability. The technology simply was not there yet. But nature had its own particle accelerator, one far more powerful than anything humans could build. Cosmic rays arrive at Earth with energies spanning an extraordinary range, from millions of electron volts to, in extreme cases, more than 100 billion electron volts. The most energetic cosmic rays carry as much energy as a professionally thrown baseball, concentrated into a single subatomic particle. No laboratory on Earth in the 1930s, or even today, can match the most energetic cosmic rays. When these particles slam into atoms in the upper atmosphere, they produce cascades of secondary particles at energies far exceeding what any terrestrial machine of that era could achieve. These cascades were a natural laboratory for high-energy physics, delivered free of charge from the depths of space. This is why Anderson was on a mountaintop with a cloud chamber, rather than in a modern laboratory with a gleaming accelerator. The sky was his accelerator, the atmosphere was his target, and the cloud chamber was his camera, capturing the tracks of whatever emerged from the collisions. He could not control what arrived. He could not aim the beam or choose the energy. He simply watched and recorded whatever nature chose to send him. The positron's discovery was therefore partly a matter of patience and luck, the right particle arriving at the right time in the right detector. But it was also a matter of preparation. Anderson had built his apparatus with great care, positioning the lead plate, calibrating the magnetic field, and understanding exactly how different particles would behave in his chamber. When the unexpected track appeared, he was ready to recognize it for what it was. When these particles hit the upper atmosphere, they create showers of secondary particles that rain down toward the surface. Anderson was using a device called a cloud chamber to observe these particle showers. A cloud chamber is a sealed container filled with supersaturated vapor. When a charged particle passes through the vapor, it ionizes the gas along its path, leaving a visible trail of tiny droplets. A condensation trail, like a miniature version of the contrails left by aircraft in the sky. By placing the cloud chamber inside a strong magnetic field, Anderson could determine the charge and momentum of each particle from the curvature of its trail. Positively charged particles curve one way, negatively charged particles curve the other. The tighter the curve, the lower the momentum. Anderson placed a lead plate across the middle of the chamber. When a particle passed through the lead, it lost energy. By seeing which side of the lead plate the particle entered from and how its curvature changed after passing through, he could determine the particle's direction of travel and its charge with certainty. And then he saw something that did not fit. A trail appeared in the chamber that curved the wrong way. It curved like a positively charged particle, not a negative one. But the curvature was too tight for it to be a proton. A proton, being nearly 2,000 times heavier than an electron, would leave a nearly straight trail at the energies involved. This trail curved sharply, just like an electron track, indicating a particle with the electron's tiny mass. But the curvature was in the direction of positive charge, not negative. Anderson checked his apparatus. He checked the magnetic field orientation. He checked everything. The result held. He was looking at a particle with the mass of an electron and a positive electric charge. He had found Dirac's anti-electron. But Anderson did not arrive at this conclusion carelessly. He was a meticulous experimentalist, and he knew that extraordinary claims require extraordinary evidence. Before announcing that he had found a new particle, he systematically eliminated every other possibility he could think of. Could the track be a proton? No. A proton is nearly 2,000 times heavier than an electron. At the energies involved in the cloud chamber observation, a proton would leave an almost perfectly straight track. The curvature would be negligible. This track curved sharply, indicating a particle with a very small mass. Could the magnetic field have been reversed, so that a normal electron track was simply curving in the expected direction for its charge, but appeared reversed? Anderson checked. The magnetic field orientation was correct. He verified it independently. The curvature genuinely indicated positive charge. Could the particle have been traveling in the opposite direction from what he assumed, entering the chamber from below rather than above? This is where the lead plate became crucial. The particle lost energy as it passed through the lead. Energy loss means the track curves more tightly after passing through the plate, because a slower particle bends more easily in a magnetic field. By observing which side of the plate showed the tighter curvature, Anderson could determine the direction of travel with certainty. The particle was definitely moving from below the plate to above it, and it was definitely curving in the direction of positive charge. Anderson considered whether it could be some kind of unusual nuclear fragment, a piece of a shattered atom carrying positive charge. But nuclear fragments are heavy. They would not curve so tightly, and they would leave thicker, denser trails in the cloud chamber, because heavier particles ionize more gas along their path. This trail was thin and delicate, exactly like an electron trail, except for the direction of its curvature. Every alternative failed. The only explanation that fit all the evidence was a particle with the electron's mass and a positive charge. Anderson had not been looking for it. He had not set out to confirm Dirac's prediction. In fact, he was not even particularly familiar with Dirac's theoretical work at the time. He found the positron the hard way, through careful observation and rigorous elimination of alternatives. The theory and the experiment converged independently, which made the discovery all the more convincing. Anderson called it the positron, a combination of positive and electron. The name stuck. Just months after Anderson's discovery, in 1933, Patrick Blackett and Giuseppe Occhialini confirmed his findings with even stronger evidence, photographing not just single positron tracks, but the simultaneous creation of electron-positron pairs from high-energy photons interacting with matter. The theoretical and experimental triumphs were recognized swiftly. Dirac received the Nobel Prize in Physics in 1933, largely for the prediction that made the discovery possible. Anderson received his in 1936. This was pair production, the birth of a particle and its antiparticle from pure energy. It confirmed that positrons were real, reproducible, and behaved exactly as Dirac's theory predicted. So what is a positron? Let us be precise, because precision matters here. A positron is a fundamental particle. It is not made of quarks. It is not made of smaller pieces. It has no known internal structure. As far as every experiment and every theory in modern physics can determine, the positron is a single, indivisible point of existence. It belongs to a family of particles called leptons. The electron is also a lepton, so are the muon, the tau, and the 3 types of neutrino. Leptons are one of the 2 main categories of matter particles in the Standard Model, the other category being quarks. The positron is specifically the antiparticle of the electron. This is its defining identity. It has the same mass as the electron, exactly the same. Not approximately the same, not close to the same, but identical down to the furthest decimal place we have ever measured. The electron's mass is roughly 511 kiloelectron volts divided by c². and the positron's mass is precisely the same value. It has the same spin as the electron, spin 1/2. It obeys the same fundamental forces. It interacts through electromagnetism. It interacts through the weak nuclear force. It feels gravity. In almost every measurable way, the positron is the electron's twin. But there is one difference. The positron carries positive electric charge where the electron carries negative charge. The magnitude is identical, one elementary unit, but the sign is flipped. And this single difference, this reversal of charge, is the reason a positron can do something no electron can. It can meet an electron and both of them can vanish. But do not let the drama of that statement mislead you. The positron is not exotic. It is not a substance from another dimension. It is not made of some opposite form of energy. It is not rare in any cosmic sense. Positrons are produced all the time naturally. They are created in certain types of radioactive decay. They are produced when cosmic rays strike the atmosphere, which is exactly how Anderson first detected one. They are generated in the cores of stars during specific nuclear reactions. They even appear routinely in hospitals. Positron emission tomography, the medical imaging technique known as a PET scan, works by injecting a patient with a radioactive substance that emits positrons. Those positrons travel a short distance through tissue, meet electrons in the body, and annihilate. The annihilation produces gamma rays that detectors pick up to create detailed images of the body's internal structures. Positrons are not hypothetical. They are practical. They are useful. They are well understood. They are a standard, verified, experimentally confirmed part of the physical universe. And here is something crucial to understand. The positron is not alone in being an antiparticle. Dirac's discovery opened a door that turned out to lead to an entire mirror world. Every particle in the Standard Model has a corresponding antiparticle. The electron has the positron. The proton, which is made of quarks, has the antiproton, which is made of antiquarks. The neutron has the antineutron. Neutrinos have antineutrinos. For every type of matter particle that exists, there is a corresponding antimatter partner with the same mass and opposite charge. Some particles that carry no charge, like the photon, are their own antiparticles. The photon and the antiphoton are the same object. But for every charged matter particle, the antiparticle is a distinct entity with the opposite sign of charge. This symmetry runs deep. It is not an accident or a coincidence. It is a mathematical requirement. When you combine quantum mechanics with special relativity, when you write down equations that respect both frameworks simultaneously, antiparticles emerge automatically. You cannot avoid them. They are not optional. They are demanded by the structure of the theory. Dirac stumbled upon this with his equation for the electron, but the principle turned out to be universal. Every quantum field that describes a charged particle necessarily contains both the particle and its antiparticle as different modes of excitation. Now, let us sit with what we have established so far. We have a particle, the positron, that is the perfect mirror image of the electron in almost every respect. Same mass, same spin, same strength of electric charge, but with the sign of that charge reversed. It was predicted mathematically before it was ever observed, and its discovery was one of the great triumphs of 20th century physics. It confirmed that the deepest equations of nature are telling the truth, even when they predict things no one expected. The positron is not composite. It is not made of anything smaller, at least not according to any theory or experiment we currently have. In the Standard Model of particle physics, the most successful and precisely tested theory of fundamental particles ever constructed, the positron is treated as an elementary object, a point-like excitation of a quantum field with no substructure. This does not mean it is impossible that someday, with more powerful experiments or a deeper theory, we might discover that positrons do have internal parts. History has taught us to be humble about such claims. Atoms were once thought to be indivisible. Then we found electrons inside them. Protons were once thought to be fundamental. Then we found quarks inside them. It is conceivable that what we now call fundamental particles might turn out to have structure at scales far smaller than we can currently probe. But as of right now, based on everything we know, the positron is fundamental. It is a basic ingredient of the universe, not a composite assembled from other ingredients. And that makes the mystery of what it does even more striking. Because this fundamental particle, this twin of the electron, this object that is not exotic or mystical or made of some strange opposite substance, this ordinary member of the standard model has a remarkable property. When it encounters an electron, both particles disappear. They do not bounce off each other like billiard balls. They do not merge into a larger object. They do not fly apart damaged. They are simply gone. And in their place, energy radiates outward in the form of photons. The mass of both particles, every last fraction of it, converts entirely into electromagnetic radiation. This is not a chemical reaction. It is not an explosion in any conventional sense. It is something far more fundamental. It is the complete conversion of matter into energy, governed by the most famous equation in all of physics, E equals mc squared. But understanding why this happens, understanding what allows two particles to simply erase each other from existence, requires going deeper. It requires understanding what the positron and the electron truly are, not just as objects sitting in space, but as excitations of something more fundamental. Something that fills all of space. Something that exists even in the emptiest vacuum. The quantum field. So we know what a positron is. We know it has the same mass as the electron, the same spin, and the opposite electric charge. We know it was predicted by an equation before anyone ever saw one in a laboratory. And we know it is treated as a fundamental particle, with no known internal parts. But saying what a positron is does not explain why it is what it is. Why does it share the electron's mass so precisely? Why is its charge reversed and not some other property? And how can one universe produce two particles that are so nearly identical, yet so fundamentally opposed that contact between them erases both from existence? To answer these questions, we need to go deeper than particles. We need to understand what particles actually are. Not what they look like, not how they behave in a cloud chamber, but what they are made of at the most fundamental level. And the answer is going to sound strange. Because particles are not really things. They are events happening in something else. They are temporary ripples in an invisible ocean that fills every point in the universe. That ocean is called a quantum field. Let us build this idea carefully, because it changes everything. In everyday life, you think of the universe as a stage with actors on it. Space is the stage, particles are the actors. The particles move around on the stage, interacting with each other, colliding, combining, breaking apart. The stage itself just sits there, passive and empty, providing a backdrop for the action. This picture is intuitive, and it works well enough for chemistry and engineering and most practical purposes. But it is wrong, or rather, it is incomplete. In the deeper picture provided by quantum field theory, the stage is not passive. The stage is everything. What we call particles are vibrations of the stage itself. Imagine a perfectly calm ocean stretching in every direction, a flat, featureless surface. That calm ocean is analogous to a quantum field in its lowest energy state, what physicists call the vacuum state. Now imagine you disturb the water. You drop a stone in. A ripple forms, a localized disturbance that moves outward, carrying energy. That ripple is not a separate thing added to the ocean. It is the ocean, temporarily organized into a moving pattern. The ripple is made of water. Take away the water and the ripple cannot exist. It has no independent identity apart from the medium it exists in. A particle, in quantum field theory, is like that ripple. It is a localized excitation of a quantum field, a temporary concentration of energy and momentum in a specific region of the field. The field is the fundamental entity. The particle is just something the field does. This idea was developed over several decades in the middle of the 20th century. Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga each independently constructed the mathematical framework for quantum electrodynamics, often abbreviated QED, which describes how electrons and photons interact. Their work earned all three the Nobel Prize in 1965. Quantum electrodynamics was the first successful quantum field theory, and it remains the most precisely tested theory in all of science. Some of its predictions match experimental measurements to better than 10 decimal places. That is like predicting the distance from New York to Los Angeles and being accurate to within the width of a single human hair. The success of QED established quantum field theory as the language of modern particle physics, and every particle in the Standard Model is now understood as an excitation of its corresponding quantum field. Here is the critical point for understanding the positron. There is not one field for the electron and a separate field for the positron. There is a single field, called the electron field, and it supports two types of excitation. One type of excitation produces an electron. The other type produces a positron. Both come from the same underlying entity. Both are ripples in the same ocean. The difference between them is not a difference in substance or composition. It is a difference in the mode of vibration. Think of a guitar string. When you pluck it, it vibrates and produces a sound. But a guitar string can vibrate in different ways. It can vibrate in its fundamental mode, producing a particular note. Or it can vibrate in higher harmonics, producing different notes. The same string, the same physical object, producing different sounds depending on how it vibrates. The electron field is somewhat analogous. It is a single mathematical object that pervades all of space. When it is excited in one way, the excitation carries negative electric charge, and we call it an electron. When it is excited in the mathematically opposite way, the excitation carries positive electric charge, and we call it a positron. Same field, different excitation, different particle. This is why the positron has the same mass as the electron. It is not a coincidence. It is not something that needs to be fine-tuned or adjusted. It is an automatic consequence of the fact that both particles come from the same field. The mass of a particle in quantum field theory is determined by the properties of its field, specifically by how the field interacts with other fields in the universe. The most important of these interactions for determining mass is the interaction with the Higgs field. The Higgs field is another quantum field that fills all of space, much like the electron field. It was first proposed theoretically in 1964 by several physicists, including Peter Higgs and François Englert, and its corresponding particle, the Higgs boson, was finally discovered at CERN in 2012. That discovery was one of the landmark moments in the history of physics. For nearly half a century, the Higgs field had existed only as a mathematical proposal, a theoretical device that made the equations of the Standard Model work correctly. Without it, the equations predicted that all fundamental particles should be massless, zipping around at the speed of light like photons. Obviously, that is not what we observe. Electrons have mass. Quarks have mass. The W and Z bosons that carry the weak nuclear force have mass. Something had to be giving them that mass, and the Higgs field was the proposed answer. But proposing a field and proving it exists are very different things. Proof required finding the Higgs boson, the particle-like excitation of the Higgs field, which demanded a particle accelerator powerful enough to produce it. The Large Hadron Collider at CERN, a 27-kilometer ring straddling the border between Switzerland and France, was built in large part for this purpose. When two independent detector teams at CERN announced in July of 2012 that they had found the Higgs boson, it confirmed that the invisible field responsible for giving the electron and the positron their mass was not just a mathematical convenience. It was real. It fills all of space, and every electron and every positron moving through the universe is wading through it, acquiring mass with every step. The Higgs field gives mass to fundamental particles through a mechanism that works roughly like this. As a particle moves through space, it interacts with the Higgs field. This interaction creates a kind of resistance, a drag, that makes the particle behave as though it has mass. The stronger the particle's coupling to the Higgs field, the more massive it appears. A particle that does not interact with the Higgs field at all, like the photon, has zero mass and moves at the speed of light. A particle that interacts strongly, like the top quark, has an enormous mass. Now here is what matters for the positron. The coupling between the electron field and the Higgs field is a property of the electron field itself. It is not a property of any individual particle. When the electron field vibrates in the mode that produces an electron, that excitation couples to the Higgs field with a certain strength. When the same field vibrates in the mode that produces a positron, that excitation couples to the Higgs field with the same strength. The coupling does not change when you flip the mode of excitation. It is built into the field, not into the particle. Therefore, both excitations acquire the same mass. The electron and positron have identical mass because they are two expressions of the same field interacting with the Higgs field in the same way. This is not something physicists have to assume or impose by hand. It falls out of the mathematics automatically. When you write down the equations of quantum field theory respecting special relativity and quantum mechanics, mass equality between particle and antiparticle is guaranteed. You cannot avoid it. It would require deliberately breaking the mathematical structure of the theory to make the masses different. And if you did that, the theory would become inconsistent. It would make predictions that contradict themselves. The equal mass of the electron and positron is therefore not a mystery. It is a consequence of the deepest mathematical principles underlying all of particle physics. But if the masses are the same, why is the charge different? Why does the positron carry positive charge while the electron carries negative charge? The answer lies in something called charge conjugation. Charge conjugation is a mathematical operation. It is a transformation you can perform on the equations of quantum field theory. When you apply charge conjugation to the description of a particle, you get the description of its antiparticle. Every property that is associated with a conserved quantum number gets flipped. Electric charge flips from negative to positive, or positive to negative. A quantum property called lepton number flips from +1 to -1. If the particle carries any other internal charges, those flip too. But crucially, some properties do not flip under charge conjugation. Mass stays the same. Spin stays the same. The magnitude of the electric charge stays the same, only the sign reverses. These properties are symmetric under charge conjugation, meaning they are the same for the particle and the antiparticle. Why does charge flip while mass does not? Because they are different types of property, rooted in different aspects of the field. Mass, as we just discussed, comes from how the field couples to the Higgs field. This coupling is a property of the field itself, not of the sign of the excitation. Whether the field vibrates in the particle mode or the antiparticle mode, it is the same field coupling to the same Higgs field in the same way. So the mass is the same. Electric charge, on the other hand, is related to a different type of symmetry. In the mathematics of the Standard Model, electric charge arises from a symmetry called U1 gauge symmetry. Without going too deeply into the mathematics, what this means is that the electron field has a kind of internal direction, a phase, and the way this phase interacts with the electromagnetic field is what we experience as electric charge. When you flip the mode of excitation from particle to antiparticle, this internal phase reverses. The coupling to the electromagnetic field reverses. The charge flips. The Higgs coupling does not care about this internal phase. It couples to the magnitude of the field's excitation, not to its direction. So mass stays the same. But the electromagnetic coupling does care about the phase. It distinguishes between the two modes. So charge reverses. Let me try to make this less abstract with an analogy, although no analogy is perfect. Imagine you have a rope tied to a wall at one end. You hold the other end. You flick the rope upward, sending a wave pulse along it. The pulse travels toward the wall, bounces off, and comes back. But when it comes back, it is inverted. Where the original pulse went up, the reflected pulse goes down. The pulse and its reflection have the same shape. They travel at the same speed. They carry the same energy. But they are upside down relative to each other. They are opposite in one specific way, while being identical in every other way. In this analogy, the upward pulse is like an electron, and the downward pulse is like a positron. They are the same type of disturbance in the same medium, carrying the same energy, but displaced in opposite directions. The direction of displacement is like the electric charge. It flips. The speed and shape of the pulse are like the mass and spin. They do not flip. This analogy is imperfect because particles are quantum objects with far richer structure than rope pulses, but it captures the essential idea. The positron is not made of different stuff from the electron. It is made of the same stuff, vibrating in the opposite sense. There is a deep theoretical result that ties all of this together. It is called the CPT theorem. CPT stands for charge conjugation, parity, and time reversal. The theorem, proven independently by several physicists in the 1950s, states that any quantum field theory that is consistent with both special relativity and quantum mechanics must be invariant under the combined operation of all three transformations performed simultaneously. That is, if you take any physical process, flip all charges, mirror all spatial coordinates, and reverse the direction of time, the resulting process must also be a valid physical process. The CPT theorem has enormous consequences. One of the most important is that it absolutely guarantees that every particle must have a corresponding antiparticle with the same mass and opposite charge. This is not a guess or an assumption. It is a mathematical theorem derived from the foundational principles of modern physics. If you accept quantum mechanics and special relativity, and you must accept them because they are confirmed by mountains of experimental evidence, then antiparticles are inevitable. The positron must exist. Its mass must equal the electron's mass. Its charge must be opposite. The CPT theorem demands it. You cannot have a consistent physical theory without it. Now, let us pause and consider what all of this means for the nature of the positron. The positron is not a separate substance injected into the universe alongside the electron. It is not made of opposite matter or reverse energy or any such thing. It is a different excitation of the same quantum field that produces the electron. The electron field is a single mathematical entity that fills all of space. It is always there, even in the emptiest vacuum. When this field is in its lowest energy state, its ground state, it produces no particles at all. The vacuum is simply the field sitting quietly, fluctuating gently as quantum mechanics requires, but not producing anything we would detect as a particle. When energy is added to the field in one particular way, the field responds by producing an electron, a localized excitation carrying negative charge, lepton number +1, and a specific mass determined by the Higgs coupling. When energy is added in the opposite way, the field responds by producing a positron, a localized excitation carrying positive charge, lepton number -1, and the exact same mass. The two particles are two sides of the same coin, two verses of the same song, two opposite modes of the same vibrating field. This perspective also explains something that Dirac's original Hole theory could not fully capture. In Dirac's picture, the positron was a hole in an infinite sea of negative energy electrons. That picture was brilliant for its time, and it gave the right answers for many calculations, but it was awkward. It required an infinite number of invisible electrons filling all of space. It made the vacuum seem incredibly complicated, filled with an undetectable ocean of particles. Quantum field theory replaces this with something cleaner. The vacuum is simply the ground state of the field. No infinite sea, no hidden particles. Just the field in its lowest energy configuration. Particles and antiparticles are excitations above this ground state. They are created when energy is added, and destroyed when the excitations interact in ways that return the field to its ground state. This is a much more satisfying picture, and it is the one modern physics relies on. But even in its lowest energy state, the field is not perfectly still. This is one of the most counterintuitive consequences of quantum mechanics. The Heisenberg uncertainty principle guarantees that no quantum field can sit in a state of perfect, motionless calm. There must always be fluctuations, tiny random disturbances in the field's energy, even in the emptiest possible vacuum. These fluctuations are called vacuum fluctuations, and they have measurable physical consequences. They are not metaphorical or theoretical. They are real, confirmed by precision experiments. One consequence of vacuum fluctuations is the constant fleeting appearance of what physicists call virtual particles. At every point in space, at every moment, the electron field is briefly flickering into tiny excitations that resemble electron-positron pairs. These virtual pairs pop into existence, borrowing energy from the vacuum for an incredibly short time allowed by the uncertainty principle, and then vanish again, returning the borrowed energy before the universe can notice the debt. They exist for durations so short that they cannot be directly observed as individual particles. They leave no tracks in detectors. They do not travel macroscopic distances. They appear and disappear within timescales of roughly 10 to the negative 21 seconds or shorter. And yet, their collective effect is measurable. Virtual electron-positron pairs slightly alter the electromagnetic field around real charged particles, producing a tiny shift in the energy levels of hydrogen atoms called the Lamb shift, which has been measured with extraordinary precision and matches the predictions of QED perfectly. They also produce a measurable force between two uncharged metal plates placed very close together, called the Casimir effect. The plates restrict which virtual fluctuations can occur between them, creating a pressure difference that pushes the plates together. This force has been measured in laboratories and agrees with theoretical predictions. What this means for the positron is profound. The positron is not some alien visitor intruding into a matter-only universe. The electron field is already producing ghostly positron-electron pairs everywhere, at every point in space, all the time. The vacuum is seething with the potential for positrons. Under normal conditions, these virtual pairs never become real because they lack the energy to persist. But add enough energy, through a high-energy photon, a radioactive decay, or a cosmic ray collision, and those virtual fluctuations can be promoted into real, lasting, detectable particles. The positron is always lurking in the quantum vacuum, waiting for the energy that will make it real. There is another consequence of this field-based understanding that is worth emphasizing. The positron does not contain extra energy or carry some hidden destructive payload. People sometimes imagine that antimatter is like some kind of explosive substance, inherently dangerous in the way that dynamite or nuclear fuel is dangerous. But this is misleading. A positron at rest has exactly the same energy content as an electron at rest. Their rest mass energy is identical, 511 kiloelectron volts each. A positron just sitting there, not interacting with anything, is no more energetic and no more dangerous than an electron just sitting there. The energy that gets released during annihilation does not come from the positron alone. It comes from both particles, the electron and the positron together. Their combined mass converts into energy. Neither particle is a bomb. Neither particle contains hidden fuel. They are simply two excitations that, when they come together, are allowed by the laws of physics to transition into a different form. The field can go from having one electron excitation and one positron excitation to having no matter excitations at all, releasing the equivalent energy as photons instead. The energy was always there. It was the mass energy of both particles. Annihilation simply converts that mass energy into a different form, electromagnetic radiation. Nothing is created from nothing. Nothing is destroyed into nothing. Energy is conserved perfectly. It just changes from one type, mass, to another type, radiation. This point deserves repetition because it is so commonly misunderstood. When a positron annihilates with an electron, the total energy before and after is exactly the same. The total momentum before and after is exactly the same. Every conserved quantity is preserved. Annihilation is not destruction in any absolute sense. It is transformation. The field goes from one configuration to another, from matter excitations to radiation excitations, from particles with mass to photons without mass. The bookkeeping is perfect. Nature does not lose track of anything. If you think about it from the perspective of the quantum field, what happens during annihilation is not strange at all. The electron and positron are opposite excitations of the same field. When they come together, they cancel each other out. The field returns to its ground state in that region of space, and the energy that was sustaining those excitations has to go somewhere. It goes into photons, which are excitations of a different quantum field, the electromagnetic field. One field settles down, another field gets excited. Energy flows from one field to another. It is elegant. It is clean. It is not mysterious. It is simply the natural behavior of quantum fields. And here is where we can draw a sharp line between what a positron is and what it is not. A positron is not made of anti-energy. There is no such thing as anti-energy in physics. Energy is energy. It is always positive, always conserved, always the same regardless of whether it is carried by matter or antimatter. A positron is not an electron travelling backward in time, despite a famous and often repeated claim. Feynman showed in his work on QED that antiparticles can be mathematically described as particles moving backward in time through the equations. This is a useful computational trick. It simplifies certain calculations enormously, but it is a feature of the mathematics, not a statement about physical reality. Positrons do not experience time in reverse. They exist in the present, interacting with other particles in the normal forward direction of time, just like everything else. A positron is not a hole in the fabric of space. Dirac's hole theory, while historically important, has been superseded by quantum field theory. The positron is a real, positive energy excitation of the electron field, not an absence of something else. What a positron is, in the clearest and most accurate language modern physics can offer, is this. It is a fundamental excitation of the electron field, carrying positive electric charge, lepton number -1, spin 1/2, and a mass of 511 kilo-electron-volts divided by c². It is the charge conjugate partner of the electron, related to it by the CPT symmetry that lies at the foundation of all quantum field theories. Its existence is required by the mathematical consistency of any theory combining quantum mechanics and special relativity. Its properties, mass, spin, and the magnitude of its charge, are identical to the electrons because both arise from the same field. Its charge is opposite because charge conjugation reverses the internal phase of the field's excitation while leaving the coupling to the Higgs field unchanged. The positron is ordinary. It obeys the same laws of physics as everything else. It is made of the same type of quantum field stuff as the electron. It exists comfortably within the Standard Model, predicted, measured, and used in practical technology every day around the world. And yet, this ordinary particle has an extraordinary ability. When it meets an electron, both particles can cease to exist as matter and transform entirely into light. Understanding why that happens, understanding the mechanism of annihilation itself, requires us to look closely at the moment of contact between these two mirror particles. What occurs in that instant, and what laws govern the transformation, is what we need to understand. Because the process of annihilation is not violent or destructive in the way most people imagine, it is precise, it is elegant, and it reveals something profound about the nature of matter itself. That matter is not permanent, it is not indestructible, it is not the solid, dependable foundation we instinctively believe it to be. Matter is temporary, it is a state of the field, and when conditions allow, the field can simply choose a different state. Picture the scene at the smallest possible scale. An electron is drifting through matter, one of trillions doing what electrons always do, orbiting a nucleus, flowing through a wire, sitting in the outer shell of an atom in your body. It is going about its ordinary business, carrying its tiny negative charge, participating in the electromagnetic interactions that hold atoms together and make chemistry possible. Nothing unusual, nothing dramatic. Then, from somewhere nearby, a positron appears. Perhaps it was produced by the decay of a radioactive nucleus. Perhaps it was born when a high-energy cosmic ray slammed into an atom in the upper atmosphere, and some of the collision energy converted into an electron-positron pair. However it got there, it is here now, a positively charged particle with the same mass as the electron, moving through the same region of space. And now, something begins to happen. The electron carries negative charge. The positron carries positive charge. Opposite charges attract. This is the same electromagnetic force that holds electrons in orbit around nuclei, the same force that makes magnets stick to refrigerators, the same force that creates lightning and radio waves, and the glow of every star. It is one of the four fundamental forces of nature, and it reaches across space at the speed of light. As the positron enters the vicinity of the electron, both particles feel the pull. The positron is drawn toward the electron. The electron is drawn toward the positron. They begin spiraling toward each other, pulled together by the electromagnetic attraction between their opposite charges. In some cases, this process happens almost immediately. The positron arrives with enough energy and at close enough range that the two particles come into contact within a tiny fraction of a second. In other cases, something remarkable happens first. The electron and positron can actually form a bound state. They orbit each other briefly, held together by the same electromagnetic force that binds an electron to a proton in a hydrogen atom. This exotic atom is called positronium. It is a real, observed, experimentally studied system. It consists of one electron and one positron orbiting their common center of mass. Positronium has no nucleus. It is held together entirely by the electromagnetic attraction between the two particles. It has energy levels and spectral lines, just like hydrogen. Physicists have measured its properties with extraordinary precision, and those measurements match the predictions of quantum electrodynamics beautifully. Positronium is worth dwelling on because it is one of the strangest and most beautiful objects in all of physics. It is an atom with no nucleus. In a hydrogen atom, the electron orbits a proton that is nearly 2,000 times heavier. The proton sits almost motionless at the center, while the electron whirls around it. But in positronium, the two particles have exactly the same mass. Neither one sits at the center. Instead, both the electron and the positron orbit their common center of mass, circling each other like two dancers holding hands and spinning, each one tracing a path of equal size on opposite sides of the center point. Positronium comes in two distinct forms, determined by how the spins of the electron and positron are aligned. If the two particles have opposite spins, the total spin of the system is 0. This form is called parapositronium. If the two particles have parallel spins, the total spin is 1. This form is called orthopositronium. The distinction matters enormously, because the spin configuration determines how the system is allowed to decay. Parapositronium, with total spin 0, decays into 2 gamma-ray photons. This happens very quickly, in about 125 picoseconds. That is 125 trillionths of a second. The system barely has time to complete a single orbit before annihilation occurs. Orthopositronium, with total spin 1, cannot decay into 2 photons. This is because of a conservation law related to a quantum property called charge conjugation symmetry. A 2-photon state has even charge conjugation parity, but orthopositronium has odd charge conjugation parity. The two do not match. Therefore, orthopositronium must decay into at least 3 photons to satisfy the conservation law. 3-photon decay is a more complex process, and complex processes take longer. Orthopositronium survives for about 142 nanoseconds, roughly 1,000 times longer than parapositronium. This is still an extraordinarily short time by human standards, but it is long enough for physicists to study the system in great detail. The energy levels of positronium have been calculated using quantum electrodynamics and measured experimentally with remarkable precision. The agreement between theory and experiment is spectacular. The ground state energy, the fine structure, the hyperfine splitting between parapositronium and orthopositronium, all of these have been measured to many decimal places and match QED predictions beautifully. Positronium serves as one of the purest testing grounds for quantum electrodynamics because it is a purely leptonic system. There are no quarks, no strong nuclear force, no nuclear structure effects to complicate the calculations. It is just an electron, a positron, and the electromagnetic force between them. Nothing else. This makes the theoretical calculations cleaner and the experimental comparisons more direct than for almost any other atomic system. Positronium also played a crucial role in confirming that annihilation follows the rules physicists expected. By measuring the number of photons produced when positronium decays and comparing the 2-photon and 3-photon decay rates for parapositronium and orthopositronium respectively, physicists verified that the conservation laws governing annihilation work exactly as predicted. The measurements confirmed charge conjugation symmetry in electromagnetic interactions to extraordinary accuracy. If any of these conservation laws were even slightly violated, the decay rates would differ from predictions, and the discrepancy would show up in the data. No such discrepancy has ever been found. But positronium does not last. It cannot last. Unlike a hydrogen atom, where the electron and proton are different types of particles and cannot annihilate each other, the electron and positron in positronium are each other's antiparticle. They are opposite excitations of the same quantum field. And so, after a brief existence, the electron and positron in positronium inevitably find each other. Whether it takes a fraction of a nanosecond or just over 100 nanoseconds depends on the spin configuration, but the outcome is always the same. They come together, and then they are gone. What happens at that moment of contact is one of the cleanest, most precisely understood processes in all of physics. Let us walk through it step by step. The electron has a mass of 511 kilo-electron-volts divided by c squared. The positron has the same mass, 511 kilo-electron-volts divided by c squared. When they meet, their combined mass is 1022 kilo-electron-volts divided by c squared, which is roughly 1.022 mega-electron-volts divided by c squared. According to Einstein's relationship E equals mc squared, this mass is equivalent to 1.022 mega-electron-volts of energy. That energy has to go somewhere. It does not disappear. Energy cannot be created or destroyed. This is one of the most fundamental principles in all of physics, the conservation of energy. This principle was established as a universal law of physics in the 1840s through the work of James Joule and Hermann von Helmholtz, and it has been confirmed in every experiment ever conducted at every scale of physics, from chemical reactions to nuclear processes to the behavior of black holes. Energy is conserved absolutely. So when the electron and positron vanish as matter, their mass energy must appear in some other form. And it does. It appears as photons. Specifically, in the simplest and most common case, the electron and positron annihilate into exactly 2 gamma-ray photons. Each photon carries away 511 kilo-electron-volts of energy, corresponding to the rest mass energy of 1 electron or 1 positron. Together, the 2 photons carry away the full 1.022 mega-electron-volts, accounting for every bit of energy that was stored in the mass of both particles. But why 2 photons? Why not 1? Why not 3 or 4 or 17? The answer comes from another conservation law, the conservation of momentum. Before the annihilation, if we consider the simplest case, where the electron and positron are essentially at rest relative to each other, or very nearly so, the total momentum of the system is approximately 0. The electron is not moving much. The positron is not moving much. Their momenta roughly cancel out. After the annihilation, the total momentum must still be 0. Momentum, like energy, is conserved absolutely. A single photon always carries momentum. It moves in one direction at the speed of light. A single photon cannot have 0 momentum. Therefore, a single photon cannot account for all the energy while simultaneously satisfying momentum conservation. You need at least 2 photons flying off in opposite directions so that their momenta cancel out, adding up to 0 net momentum, matching the 0 total momentum the system had before the annihilation. This is why the 2 photons fly apart in exactly opposite directions. Not roughly opposite, exactly opposite, 180 degrees apart. If you detect one photon going to the left, you know with certainty that the other photon is going to the right. This is not a random outcome. It is dictated by the law of conservation of momentum. The 2 photons are born traveling in precisely opposite directions, each carrying 511 kilo-electron-volts of energy, each moving at the speed of light. They are gamma rays, photons with far more energy than visible light. A photon of visible light carries roughly 1.5 to 3 electron-volts of energy. These annihilation photons carry 511,000 electron volts each. They are hundreds of thousands of times more energetic than the light your eyes can detect. This is the foundation of positron emission tomography, the medical imaging technology used in hospitals around the world. A patient is injected with a substance labeled with a radioactive isotope, often fluorine-18, which emits positrons when it decays. Each emitted positron travels a very short distance through the body, typically less than a millimeter, before encountering an electron in the surrounding tissue. The positron and electron annihilate, producing two gamma-ray photons that fly apart in opposite directions. Detectors arranged in a ring around the patient pick up both photons nearly simultaneously. Because the photons travel in exactly opposite directions, the detector system can draw a straight line between the two detection points and know that the annihilation happened somewhere along that line. By collecting millions of such events and using computer algorithms to process the data, a detailed three-dimensional image of the body's internal activity is constructed. Let me walk you through a specific example to make this concrete. Imagine a patient suspected of having cancer. Certain types of cancer cells are metabolically hyperactive. They consume glucose, a simple sugar, at a much higher rate than normal healthy tissue. Doctors exploit this by injecting the patient with a glucose molecule that has been modified. One of its atoms has been replaced with fluorine-18, a radioactive isotope that emits positrons when it decays. The modified glucose, called fluorodeoxyglucose, circulates through the body in the bloodstream. Cells throughout the body absorb it, just as they absorb normal glucose. But cancer cells, hungry for fuel, absorb far more of it than surrounding healthy tissue. The fluorine-18 atoms inside the cancer cells are unstable. Each one eventually decays, emitting a positron. That positron travels a very short distance through the surrounding tissue, typically less than a millimeter, losing energy as it goes, bumping into atoms and slowing down. Within a fraction of a nanosecond, it encounters an electron in the tissue. The two particles annihilate. Two gamma-ray photons fly apart in exactly opposite directions, each carrying 511 kiloelectron volts of energy. The photons pass through the body and strike detectors arranged in a ring around the patient. The detection system registers both photons arriving within a few nanoseconds of each other on opposite sides of the ring. The computer draws a line between the two detection points and records that an annihilation event occurred somewhere along that line. Over the course of the scan, which typically takes 15 to 30 minutes, millions of such events are recorded. Millions of positrons are emitted, millions of annihilations occur, millions of photon pairs are detected. The computer processes all of these lines, finding where they intersect most densely. Regions where many lines converge correspond to regions where many annihilations occurred, which correspond to regions where a lot of fluorodeoxyglucose accumulated, which correspond to regions of high metabolic activity. Cancer shows up as a bright spot on the image, a concentrated cluster of annihilation events, revealing a tumor that might be invisible to other imaging techniques. The physics of positron-electron annihilation, discovered through cosmic ray experiments in the 1930s, is now a routine, life-saving medical tool, used in thousands of hospitals worldwide every single day. The technology works precisely because the physics of annihilation is so clean and predictable. Two photons, opposite directions, 511 kiloelectron volts each, every single time. Now, I said the simplest case produces two photons. That is the most common outcome by far, but it is not the only possibility. If the electron and positron are approaching each other with significant kinetic energy, if they are moving fast when they collide, the total energy of the system is greater than just the rest mass energy. The extra kinetic energy must also be accounted for after the annihilation. In such cases, 3 or more photons can be produced. The angular relationships become more complex. The photons do not necessarily travel in exactly opposite directions, but the total energy and momentum are still perfectly conserved. Every photon carries away some fraction of the total energy and momentum, and it all adds up precisely. At very high energies, electron-positron annihilation can produce not just photons, but other particles entirely. If the total energy is high enough, the annihilation can produce muon-antimuon pairs, quark-antiquark pairs that quickly form composite particles called hadrons, or even heavier exotic particles. The key requirement is that the total energy must be sufficient to create the mass of the new particles, according to E equals mc squared, and all conservation laws must be satisfied. This is precisely what particle accelerators like the Large Hadron Collider exploit. By smashing particles together at enormous energies, physicists create conditions where the collision energy converts into the mass of new, often heavy and short-lived particles that would never appear under ordinary conditions. The same fundamental process, the conversion of energy from one form to another, governed by conservation laws, operates whether you are observing a quiet annihilation in a hospital PET scanner or a violent collision in a particle accelerator. Let us now draw a sharp distinction between annihilation and other types of destruction you might be familiar with. This distinction matters because most people, when they hear that matter is destroyed during annihilation, picture something like an explosion. They think of bombs or fire or nuclear reactions. But annihilation is fundamentally different from all of these, and understanding the difference reveals something deep about what matter actually is. Start with chemical reactions. When you burn a piece of wood, you are breaking and forming chemical bonds. The carbon in the wood combines with oxygen from the air to produce carbon dioxide and water. Energy is released in the form of heat and light, but no atoms are destroyed. Every carbon atom that was in the wood still exists after the fire. It is now part of a carbon dioxide molecule floating in the air. Every oxygen atom, every hydrogen atom, every atom of every element is still there. They have simply rearranged. The total number of protons, neutrons, and electrons before the fire is exactly the same as the total number after. Matter has not been destroyed, it has been rearranged. The energy released comes from the difference in binding energy between the original molecules and the product molecules. The atoms have moved from a higher energy configuration to a lower energy configuration, and the difference is released as heat. This is what chemistry is: rearranging atoms. No atom is ever destroyed in a chemical reaction. Not one. Now consider nuclear fission, the process that powers nuclear reactors and atomic bombs. When a uranium nucleus absorbs a neutron and splits into two smaller nuclei, it releases an enormous amount of energy, far more than any chemical reaction. But even here, matter is not truly destroyed. The protons and neutrons that made up the uranium nucleus still exist. They are now arranged into two smaller nuclei, plus a few free neutrons. What has changed is the binding energy. The total mass of the products is very slightly less than the total mass of the original uranium nucleus plus the absorbed neutron. That tiny difference in mass, less than 1%, has been converted into energy according to E equals mc squared. The protons and neutrons themselves remain intact. No particle has been annihilated. No particle has vanished from existence. The constituents have rearranged, and a small fraction of the total mass energy has been released. Nuclear fusion, the process powering the Sun and all stars, works similarly, but in the opposite direction. Light nuclei, typically hydrogen, fuse together to form heavier nuclei, typically helium. Again, the products have slightly less mass than the ingredients, and the difference is released as energy, but no particles are destroyed. The protons and neutrons just rearrange into a different nuclear configuration, and a small mass difference is liberated as energy. The Sun converts about 4 million tons of mass into energy every second through fusion. That sounds like a lot, but it is a tiny fraction of the Sun's total mass. The Sun has been doing this for 4.5 billion years and has lost less than 1% of its mass in that time. Even in these powerful nuclear processes, the vast majority of mass remains as mass. Only a small fraction converts. Now compare all of this to electron-positron annihilation. When an electron and a positron annihilate, the situation is categorically different. No atoms rearrange, no nuclei split or merge, no tiny fraction of mass converts to energy, while the rest stays behind as matter. The entire mass of both particles, 100% of it, converts into energy. The electron is gone. The positron is gone. There are no leftover fragments, no residual protons or neutrons or quarks sitting where the particles used to be. The matter has not been rearranged. It has been entirely eliminated as matter and replaced with radiation. This is total conversion. E equals mc² applied without remainder. And the efficiency of this conversion is staggering when compared to other energy-releasing processes. In chemical reactions like burning, the fraction of mass that converts to energy is so small it is essentially unmeasurable. It exists, but it is on the order of 1 part in a billion. In nuclear fission, roughly 0.1% of the mass converts to energy. In nuclear fusion, roughly 0.7% of the mass converts. In electron-positron annihilation, 100% of the mass converts to energy. Every last fraction. Nothing is left behind. If you could somehow take 1 kilogram of electrons and 1 kilogram of positrons and bring them together, the total energy released would be approximately 180 quadrillion joules. For comparison, the atomic bomb dropped on Hiroshima released approximately 63 trillion joules. 1 kilogram of matter annihilating 1 kilogram of antimatter would release roughly 3,000 times the energy of the Hiroshima bomb, and it would do so from just 2 kilograms of material. A powerful chemical explosive like TNT, by contrast, releases only about 4.6 million joules per kilogram. Annihilation is tens of billions of times more efficient per unit mass than chemical explosives. This is why antimatter has captured the imagination of science fiction writers and weapons theorists alike. The energy density is almost incomprehensibly high, but it is essential to understand that this energy does not come from the antimatter alone. It comes equally from the matter. The positron contributes half the mass energy. The electron contributes the other half. Without ordinary matter to annihilate against, the positron just sits there, a harmless particle with the mass of an electron, not releasing any energy at all. There is another important distinction to make. Annihilation is not destruction in the everyday sense of the word. When you crush a glass, the glass is destroyed as a glass, but all its atoms remain. When you delete a file on a computer, the data is lost, but the hard drive remains. These are acts of rearrangement, or erasure of pattern, not elimination of substance. Annihilation is different. The substance itself, the matter, ceases to exist as matter. But even so, nothing is truly lost. Energy is conserved. Momentum is conserved. Every quantum number that must be conserved is conserved. The universe's books balance perfectly before and after. From the perspective of conservation laws, nothing has been destroyed. Everything that the electron and positron possessed, their energy, their momentum, the information encoded in their quantum states, all of it is carried away by the photons. The photons are not lesser products, they carry everything. They are the electron and positron's full legacy, transformed into a different physical form. This is what makes annihilation so profound and so different from every other process in everyday experience. In your daily life, you are used to the idea that matter is permanent. You break things, you burn things, you dissolve things, but the underlying atoms persist. They are reshuffled, reorganized, recombined, but they survive. This permanence feels like a fundamental feature of reality. It feels like matter is solid, dependable, indestructible at its deepest level. Annihilation shatters that intuition. It shows that matter is not permanent. Particles can come into existence and go out of existence. They can appear from energy and return to energy. The atoms you are made of feel solid and eternal, but the particles making up those atoms are not truly indestructible objects. They are excitations of quantum fields, and excitations can be created and can subside. Under ordinary conditions, the particles making up your body are perfectly stable. Electrons do not spontaneously vanish because there are no positrons around to annihilate with. Protons are extraordinarily stable, with lifetimes that may exceed the current age of the universe by many orders of magnitude. For all practical purposes, your matter is safe. But the principle remains. Matter is not a substance in the way that ancient philosophers imagined, some fundamental, indestructible material underlying all things. Matter is a state. It is one of the configurations that quantum fields can adopt. And under the right conditions, when the right conservation laws are satisfied, that configuration can change. Fields that were vibrating as matter can settle down and transfer their energy to fields vibrating as radiation. The matter is gone. The energy lives on in a different form. Let us also appreciate how precisely all of this has been measured. The energy of each photon produced in electron-positron annihilation at rest has been measured to be 511.0 kiloelectron volts, matching the known rest mass of the electron and positron with extraordinary precision. The photons are detected traveling in exactly opposite directions, confirming momentum conservation. The angular correlation between the two photons has been measured and matches the predictions of quantum electrodynamics to many decimal places. The rate at which positronium decays through annihilation has been calculated using QED and measured experimentally, and the agreement is phenomenal. These are not rough approximations. These are among the most precise measurements in all of experimental physics, and they confirm that our understanding of annihilation is correct down to the finest details. So let us summarize what actually happens at the moment of contact. An electron and a positron, drawn together by electromagnetic attraction, meet. Their opposite quantum numbers, charge, lepton number, cancel perfectly. The total charge of the system is 0. The total lepton number of the system is 0. Every quantum number that distinguishes the electron-positron system from pure radiation adds up to nothing. The system is therefore permitted to transition into photons, which carry 0 charge and 0 lepton number. The mass energy of both particles converts entirely into the energy of the photons. Two gamma rays emerge, traveling in opposite directions at the speed of light, each carrying 511 kiloelectron volts. The entire process conserves energy, momentum, charge, lepton number, and every other conserved quantity. It is clean. It is total. It is 100% efficient in converting mass to energy, and it is fundamentally different from any other energy-releasing process in nature. It is not burning. It is not fission. It is not fusion. It is not breakage or rearrangement or chemical transformation. It is the complete conversion of matter into radiation, made possible by the fact that the electron and positron are opposite excitations of the same quantum field, with quantum numbers that perfectly cancel. But this immediately raises a deeper question. Why is this allowed? Why can an electron and a positron annihilate, but two electrons meeting each other cannot? Two electrons collide all the time. They repel each other, scatter off each other, and exchange energy. But they never annihilate. They never convert into pure radiation and vanish. What is different about the electron-positron encounter that permits total annihilation, while the electron-electron encounter forbids it? The answer lies in the conservation laws themselves, in the precise quantum bookkeeping that governs every interaction in the universe. And understanding this bookkeeping will reveal that annihilation is not some exotic exception to the rules. It is the rules, working exactly as they should. The question is deceptively simple. Why can an electron annihilate with a positron, but not with another electron? Both encounters involve two particles meeting. Both involve electromagnetic interaction. Both involve particles with the same mass. And yet one encounter ends with both particles vanishing into light, while the other ends with both particles bouncing away, completely intact, continuing as though nothing remarkable happened. The difference is not about energy. It is not about speed or violence or some special condition of the collision. The difference is about bookkeeping. The deepest, most unbreakable bookkeeping in the universe, the conservation laws. Conservation laws are the backbone of physics. They are the rules that nature never, under any circumstances, violates. Not once, not ever. Not in any experiment ever conducted, not in any observation ever made, not in any corner of the universe we have ever examined. They are more reliable than any other principle in science. Conservation laws hold absolutely. They are the closest thing physics has to commandments written into the fabric of reality. And they are the reason annihilation is possible between an electron and a positron, and impossible between two electrons. Let us go through them one at a time. Start with the conservation of electric charge. Electric charge is a quantity that is never created and never destroyed in any physical process. The total electric charge before an interaction must equal the total electric charge after. This is not a suggestion, it is an absolute law, confirmed by every experiment in the history of physics. When an electron meets a positron, the electron carries a charge of -1, and the positron carries a charge of +1. The total charge of the system is -1 plus +1, which equals 0. After the annihilation, the products are photons. Photons carry 0 electric charge. The total charge after the annihilation is 0. 0 before, 0 after. Charge is conserved. The annihilation is permitted by this rule. Now consider two electrons meeting. Each carries a charge of -1. The total charge of the system is -1 plus -1, which equals -2. For these two electrons to annihilate into photons, the products would need to carry a total charge of -2. But photons carry 0 charge. There is no combination of photons that adds up to -2. It is impossible. Two electrons cannot annihilate into photons because doing so would violate the conservation of electric charge. The charge has nowhere to go. It cannot vanish. It cannot be swept away. It must be accounted for, and photons cannot carry it. The reaction is forbidden. This alone would be enough to prevent electron-electron annihilation, but nature has additional safeguards. Consider the conservation of lepton number. Lepton number is a quantum number assigned to particles in the lepton family. The electron, the muon, the tau, and their associated neutrinos are all leptons. Each lepton is assigned a lepton number of +1. Each antilepton, including the positron, is assigned a lepton number of -1. Particles that are not leptons, like protons, neutrons, quarks, and photons, have a lepton number of 0. In every known interaction, the total lepton number before and after must be the same. It is conserved. When an electron meets a positron, the electron has lepton number +1 and the positron has lepton number -1. The total lepton number is +1 plus -1, which equals 0. After annihilation, the photons each have lepton number 0. Total lepton number after is 0. 0 before, 0 after. Lepton number is conserved. The annihilation is allowed. When two electrons meet, each has lepton number +1. The total lepton number is +1 + +1, which equals 2. For these two electrons to annihilate into photons, the total lepton number after would need to be 2. But photons carry 0 lepton number. No combination of photons adds up to a lepton number of 2. The reaction is forbidden. Lepton number cannot simply disappear. It must be carried by the products, and photons do not carry it. So two independent conservation laws, charge conservation and lepton number conservation, each independently forbid the annihilation of two electrons. Nature has redundant safeguards, multiple locks on the same door, ensuring that certain processes simply cannot happen. But for the electron-positron pair, every lock opens. Charge sums to 0. Lepton number sums to 0. These quantum numbers match those of photons perfectly. The system is indistinguishable, from a quantum number perspective, from a collection of photons. There is no conserved quantity preventing the transition. And so the transition happens. The matter excitations of the electron field dissolve, and the energy reappears as excitations of the electromagnetic field. It is not that some special force causes the annihilation, it is that nothing prevents it. The conservation laws, which block so many other processes, step aside completely for this one. Every conserved quantity that the electron-positron system possesses is either 0 or can be carried away by the products. The door is wide open, and nature walks through it. This perspective, that annihilation happens because nothing forbids it, is deeply characteristic of how quantum mechanics works. In quantum mechanics, anything that is not forbidden by a conservation law will eventually happen. It might happen rarely, it might happen slowly, but if the process is consistent with all conservation laws, it has a non-zero probability, and given enough time or enough interactions, it will occur. The positron and electron are not compelled to annihilate by some mysterious force of mutual destruction. They simply exist in a state that is allowed to transition into a different state, and quantum mechanics guarantees that such transitions occur. The rate at which they occur can be calculated precisely using QED, and those calculations match experiments with extraordinary accuracy. This is the power of conservation laws. They do not merely describe what happens, they prescribe what is possible and what is not. They are the ultimate gatekeepers of every process in the universe. Now, here is something that should strike you as remarkable once you think about it carefully. If an electron and a positron can annihilate into photons because all the quantum numbers sum to 0, then the reverse process should also be possible. If two photons can arrange themselves with the right energy and the right quantum numbers, they should be able to produce an electron-positron pair from nothing. And indeed, this is exactly what happens. It is called pair production, and it is the mirror image of annihilation. In pair production, a photon with sufficient energy passes near an atomic nucleus and spontaneously transforms into an electron and a positron. The photon vanishes. Two particles with mass appear where none existed before. The minimum energy required is 1.022 mega-electron volts, corresponding to the combined rest mass of one electron and one positron. Any energy beyond this minimum goes into the kinetic energy of the newly created particles. Let us walk through a specific scenario to make this vivid. Imagine a gamma-ray photon traveling through space. It has an energy of 2 mega-electron volts, nearly twice the minimum threshold needed for pair production. This photon is a ripple in the electromagnetic field, a massless packet of energy traveling at the speed of light. It carries no electric charge. It has no lepton number. By itself, in empty space, far from any other matter, this photon will continue traveling forever. Nothing will happen. Even though it carries more than enough energy to produce an electron-positron pair, it cannot do so in a vacuum because there is no way to simultaneously conserve both energy and momentum. The photon's momentum is related to its energy, and the arithmetic simply does not work for a single photon transforming into two massive particles in empty space. One of the two conservation laws will always be violated. But now imagine this photon passes close to a heavy atomic nucleus, say a nucleus of lead with 82 protons and 126 neutrons. The nucleus creates a strong electric field in its vicinity. As the photon enters this field, something extraordinary happens. The photon interacts with the electric field of the nucleus and vanishes. In its place, two particles appear, an electron and a positron, materializing out of what was pure radiation an instant before. The newly created electron curves one way in the nuclear electric field, and the newly created positron curves the other way, pulled in opposite directions by their opposite charges. The nucleus itself recoils very slightly, absorbing a tiny amount of momentum. This is the key. The nucleus acts as a momentum sink, a massive bystander that can absorb whatever leftover momentum the conservation equations require without gaining any significant energy because it is so heavy. A lead nucleus is nearly 400,000 times heavier than an electron. Absorbing a small amount of momentum barely affects it. It is like throwing a tennis ball at a freight train. The train absorbs the impact without noticeably changing its motion. Of the photon's original 2 mega-electron volts of energy, 1.022 mega-electron volts go into creating the mass of the electron and positron. The remaining energy, roughly 0.978 mega-electron volts, becomes kinetic energy shared between the two new particles and a negligible amount of recoil energy in the nucleus. The electron and positron fly apart, each one a real, detectable particle with mass and charge, born from a photon that had neither. The electromagnetic field gave up an excitation, and the electron field gained too. Energy was conserved, momentum was conserved, charge was conserved because the electron's negative charge and the positron's positive charge sum to zero, matching the photon's zero charge. Lepton number was conserved because the electron's lepton number of +1 and the positron's lepton number of -1 sum to zero. Every book balances perfectly. Nothing was borrowed, nothing was invented. The universe simply rearranged its energy from one field to another. The nucleus is needed to conserve momentum. A single photon in empty space cannot produce a pair because momentum conservation would be violated, for the same geometric reason that a single photon cannot be the sole product of annihilation. But near a nucleus, the nucleus absorbs a tiny amount of recoil momentum, and the process becomes allowed. Pair production has been observed countless times in laboratories and in nature. It happens in the atmospheres of stars, in the vicinity of black holes, in the detectors of particle accelerators, and in the upper atmosphere of Earth when high-energy cosmic rays interact with air molecules. It is not exotic or unusual. It is a standard, well-documented process that confirms one of the most profound implications of modern physics. Matter can be created from energy. Not rearranged, not reshaped, not reassembled from pre-existing components, created. A photon, which is pure electromagnetic radiation with no mass, no charge, no lepton number, enters, and an electron and a positron come out. Particles with mass, with charge, with lepton number appear where they did not exist before. The photon's energy converts into the mass and kinetic energy of the newly created particles. Annihilation and pair production are two sides of the same coin. They are the same process running in opposite directions. In annihilation, matter converts into radiation. In pair production, radiation converts into matter. Together, they demonstrate that the boundary between matter and energy is not a wall. It is a door, and it swings both ways. What we call matter and what we call radiation are not fundamentally different substances. They are different configurations of quantum fields. Under the right conditions, fields can transition from one configuration to another. Mass can become light. Light can become mass. The universe does not distinguish between these forms the way our intuition does. To the universe, they are just different states of the same underlying reality. Think about what this means. The particles that make up your body, the electrons in your atoms, the quarks inside your protons and neutrons, were not always particles. They were created. At some point in the history of the universe, the energy that now constitutes your mass was in a different form. In the first moments after the Big Bang, the universe was so hot and so dense that particles and antiparticles were being created and annihilated constantly. Photons had enough energy to produce electron-positron pairs, and those pairs were annihilating back into photons just as quickly. It was a seething equilibrium, a constant exchange between matter and radiation, back and forth, creation and destruction in an endless cycle. As the universe expanded and cooled, the photons lost energy. Eventually, they no longer had enough energy to produce new pairs. The creation side of the cycle stopped, but the annihilation side continued. Particles met antiparticles and vanished into radiation. If the universe had contained exactly equal amounts of matter and antimatter, every particle would have found a partner and annihilated. The universe would have ended up as nothing but a cooling bath of photons. No atoms, no stars, no planets, no life. Nothing but light, expanding and cooling forever. But that is not what happened. For reasons that remain one of the deepest unsolved puzzles in all of physics, the early universe contained a tiny excess of matter over antimatter. For every billion antiparticles, there were roughly 1,000,000,001 particles. When the annihilation era ended, when every antiparticle had found a partner and been converted into photons, that tiny surplus of matter remained. One particle in 1,000,000,000 left over after the Great Annihilation. And that leftover residue, that 1 in 1,000,000,000 surplus, is everything you see around you. Every star, every galaxy, every planet, every living thing, everything in the observable universe made of matter is the leftover remnant of a near total annihilation that happened in the first seconds of cosmic history. You exist because the accounting was slightly off. Because for every billion annihilations that produced nothing but light, one extra particle of matter had no partner and survived. The atoms in your body are survivors of the most thorough destruction event in the history of the universe. Why the universe had this slight surplus of matter over antimatter is unknown. It is called the baryon asymmetry problem, and it is one of the great open questions of modern physics. The Standard Model, in its current form, does not fully explain it. There are mechanisms within the Standard Model that can produce slight matter-antimatter imbalances under certain conditions, but they are far too small to account for the observed surplus. Something beyond the Standard Model, some undiscovered process or particle or symmetry violation, must be responsible. In 1967, the physicist Andrei Sakharov identified 3 conditions that any process must satisfy to produce a matter-antimatter imbalance from an initially symmetric state. First, there must exist interactions that violate baryon number conservation, meaning processes that can change the total number of baryons, particles like protons and neutrons, in the universe. Without such processes, any initial symmetry between matter and antimatter would be permanent. Second, there must be violations of 2 symmetries called C-symmetry and CP symmetry. C-symmetry, charge conjugation, is the symmetry between particles and antiparticles. CP symmetry combines charge conjugation with parity, the mirror reversal of spatial coordinates. If both C and CP symmetry were perfectly preserved, then any process producing excess matter would be exactly balanced by an equivalent process producing excess antimatter. The two would cancel and no net surplus could develop. Third, these baryon number violating, CP violating processes must occur out of thermal equilibrium. If the universe were in perfect thermal equilibrium, then every reaction would proceed at the same rate as its reverse, and no net asymmetry could build up. All three conditions must be met simultaneously. The Standard Model does contain CP violation, discovered experimentally in 1964 in the decay of certain particles called kaons. And the Standard Model does contain processes that can violate baryon number at very high temperatures through a quantum mechanical effect called a Sphaleron transition. And the expanding universe does provide a departure from thermal equilibrium. So in principle, all three Sakharov conditions can be satisfied within known physics. The problem is magnitude. The amount of CP violation in the Standard Model is far too small. It would produce a matter-antimatter asymmetry billions of times smaller than what we observe. Something else, something we have not yet discovered, must be amplifying the effect. Physicists are actively searching for this mechanism. It is one of the motivations behind next-generation particle physics experiments. Understanding why matter won over antimatter in the early universe would be one of the most significant discoveries in the history of science. And it is a question that arises directly from the physics of annihilation, from the fact that matter and antimatter destroy each other so completely that the slightest imbalance in their initial quantities determines whether a universe ends up empty or full. Let us now step back and consider the full picture of what the positron has taught us about the nature of matter. The positron was the first antiparticle ever predicted and the first ever discovered. Its existence forced physicists to confront the idea that every particle has a mirror image, an antiparticle with opposite quantum numbers. Its annihilation with the electron demonstrated that matter is not indestructible. Particles can be created and destroyed. Mass and energy are interchangeable. The boundary between substance and radiation is fluid, not fixed. The positron showed that particles are not little balls of stuff. They are excitations of quantum fields, temporary patterns of energy and quantum numbers that can appear, persist, and disappear according to rules written in the language of conservation laws. When conditions permit, when the quantum numbers add up, when every conservation law is satisfied, matter can become light, and light can become matter. This understanding transforms our concept of what it means for something to be real. In everyday experience, we think of matter as the foundation of reality. Matter is solid. It has weight. It takes up space. It persists. You can touch it. You can hold it. Energy, by contrast, seems abstract. You cannot hold a photon in your hand. You cannot weigh a beam of light on a kitchen scale. Matter feels fundamental, and energy feels secondary, a property that matter possesses rather than a thing in itself. But physics tells us the opposite. Energy is the deeper concept. Mass is a form of energy, not the other way around. When an electron and positron annihilate, what you are witnessing is energy moving from one form to another, from the mass energy of two particles to the radiative energy of two photons. The energy was there before the annihilation. It is there after. Nothing was gained, nothing was lost. It just changed shape. The particles were not containers holding energy. The particles were energy, organized into a particular pattern, a particular excitation of a particular field. When the pattern dissolved, the energy remained, carried forward by a different pattern in a different field. This is perhaps the most profound lesson of the positron. Matter is not the bedrock of existence. Matter is a costume that energy wears. Under ordinary conditions, that costume is extraordinarily stable. The electrons in your atoms will not encounter positrons under normal circumstances. There are no positrons wandering through your body looking for electrons to annihilate with. The matter you are made of is safe, not because it is indestructible, but because the conditions for its destruction are not present. There are no antiparticles in your environment. The conservation laws protect you, not by making annihilation impossible in principle, but by making it fantastically unlikely in practice. You are made of matter, and you are surrounded by matter. Antimatter is rare in the observable universe today, a consequence of that slight surplus from the first seconds of cosmic history. But the principle stands. Matter can be unmade. Not by smashing it hard enough, not by heating it enough, not by applying enough force. Those things rearrange matter. Annihilation unmakes it entirely, converting its mass completely into radiation. And the reverse process, pair production, makes matter from radiation. These processes reveal that the universe is not built from indestructible building blocks. It is built from fields, and those fields can ripple into matter or settle into radiation, depending on the circumstances. The positron is not a threat, or a weapon, or an exotic curiosity. It is a messenger. It carries a message about the nature of reality itself. It tells us that the stuff we are made of, the matter we touch and hold and stand upon, is not permanent. It is a temporary arrangement, a pattern in the quantum fields that fill all of space. A pattern that can be created, sustained, and dissolved. A pattern that emerged from the fires of the early universe and has persisted for billions of years, but that is not, in any fundamental sense, immortal. And yet, there is nothing frightening about this. The impermanence of matter does not make it less real or less valuable. A wave in the ocean is temporary. It rises, travels, and dissolves back into the water. But while it exists, it is real. It carries energy. It shapes the shoreline. It can be beautiful. The fact that it will eventually return to the calm surface does not diminish its existence while it lasts. Matter is the same. The atoms in your body are patterns in quantum fields. Those patterns have persisted for billions of years. They will persist for billions more under ordinary conditions. They are real. They carry energy. They sustain life and consciousness and everything you experience. The fact that they are, in principle, temporary configurations of something deeper does not make them less significant. It makes them more remarkable. Out of the ceaseless fluctuations of quantum fields, stable patterns emerged. Those patterns built atoms. Atoms built molecules. Molecules built cells. Cells built organisms. Organisms became aware. And one species, on one small planet, learned to ask what it is made of, and discovered that it is made of excitations in quantum fields, temporary ripples in an ocean of mathematics, patterns that know they are patterns. The positron is the key that unlocked this understanding, a particle predicted by mathematics before it was ever seen, a mirror image of the electron, identical in mass and spin, opposite in charge and lepton number, a fundamental particle with no known internal structure, arising from the same quantum field as the electron. A particle whose meeting with an electron converts both entirely into light, with 100% efficiency, governed by conservation laws that nature has never once been observed to violate. It is not exotic. It is not mystical. It is not outside ordinary physics. It is ordinary physics taken to its logical conclusion. The universe is made of fields. Fields produce particles. Particles are temporary. And when a particle meets its antiparticle, when every quantum number cancels and every conservation law gives its permission, matter returns to energy and the fields settle back to their ground state, as if nothing had ever been there at all. Except for the light. The light remains, travelling outward at 300,000 kilometers per second, carrying with it every joule of energy that the particles once possessed. The particles are gone, but their energy lives on, transformed, redistributed, woven back into the fabric of the universe. Nothing was lost. Nothing was destroyed. Everything was conserved. The universe simply changed its mind about what form that energy should take. And that, in the end, is what a positron really teaches us. Not that matter can be destroyed, but that matter was never the deepest layer of reality in the first place. Energy is, and energy, unlike matter, truly is forever.